Okay, well, now we're talking about the derivative as a function. And we've done a few of these already, but here's the derivative definition. And it's f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. As opposed to what we did before is we did a derivative at a point. And the only difference with what you did at a point was we called it, f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. So basically this was a specific point on your graph. And what we're going to be doing now is moving to this where we're going to let the x's stay in there so that we can come up with a derivative function. Then we can plug any x value we want. And this is basically a lot of algebra, and we've already been practicing this, and we're going to do some more in class on that. But what this video basically talks about is the derivative as a function. But this is our new beauteous thing we're going to use in class. So this will be nice. We're going to practice this too. Alright, so let's look at what the derivative function is. So what I have here is I have a regular graph. This is a graph of f of x. Alright, so I have a lot of points on here. So I'm going to make my point here by actually putting the points down. So we're going to do point A, B, C, D, and E here. And I went through and I basically tried to guesstimate what the points would be. So this is over here to the left and up. So this point's like -312 roughly for A. B looks like it's over here. We'll call that 3, and it goes up 10. So this is the point 310. And C looks like the point 57. D looks like the point 84. And E looks like the point 13.8. Now you said, okay, all right, so we've found these points. Now if you look at this graph here, this looks flat. So if you were to look at flat, the slope here is 0 on our graph. This one is negative, and it's a perfect -1, so the slope here is -1 at B. At C, it's a little steeper, so the slope here is -4/3. Down here, if you'll notice, see how this is flat up here, this is down here, the slope is 0 here at D also. Then it starts increasing, it's pretty steep, and they're showing you by this triangle roughly how they're estimating what the slope is, and they're saying the slope here at E looks like at 2. Okay? So they're telling you all the slopes at all the spots, and these are the actual points. Now, if I actually take these x values and plot them on and make a derivative, so this is the function f of x, and now I'm going to do the function of f prime of x. What you're really doing now is using the same x values that are here, and we're now going to put the slopes. So the slopes we looked at before, see how this was a 0 slope? It now crosses the x-axis. So now I have a prime, b prime, c prime, d prime, and e prime, and that means that they're changed, or the derivative here. The x values are all the same as they were above. I know we can't see them, but they're there. Now the y values are all the slopes. So above at A, I'm going to move this up a little bit so you can see it. See how the slope was 0 up here? That means this is a point -3, 0. Then they said the slope at B was -1, so this is 3, -1. 5, the slope is -4/3. 8, the slope is 0 again here at point D. And 13, it's positive at 2. Now if we were actually going to plot these points, your graph looks a little bit different, and this is the graph of the derivative, where this is crossing the x-axis because it crosses at 0. When the slope is negative, it goes below the x-axis. When it's a curved up there, or a max or a min, if you will, it's 0, the slope, and then when it's positive, it goes above the x-axis. So right here is the graph of the derivative of that function. So now you can actually graph it. Okay? So we made a graph of y equals f prime of x by plotting the slopes from the graph of y equals f of x in A. The vertical coordinate of b prime is the slope at B, and so on and so forth. The graph of f prime is a visual record of how the slope of f changes with x. Okay? So here basically I have the points x, y, which are now x, f prime of x. That's what's on this graph. All these are slopes. Okay, and up here we just had the regular old points of x, f of x, and or x, y's, if you will. So basically by doing that you can graph another whole function. Okay, so let's kind of write that again so we make sure we get it. The derivative function is the function created from all the slopes at the, let me fix that, at the corresponding points. Okay. All right, now let's talk about continuity and differentiability. Now we've talked about continuity before, and we always talked about, okay, a function is continuous on an interval if it's continuous at every point in the interval. And remember we said if you don't pick up your pencil, then you know it's continuous. All right? A function is differentiable if it has a derivative there. So basically, if I say it's differentiable, that means there's a derivative there. Okay? I'm just putting this just so you have this in your notes. If f of x is differentiable at x equals a, then f of x is continuous. This usually is stated as differentiability implies continuity. So, if I tell you if there's a derivative there, you can assume that it's continuous. So let's use some logic here. If I use an if-then statement, if a function is differentiable, then I can say, then it is continuous. Now, if we use the converse in logic, so here's we're using some logic here. If I use the converse and switch these, so if I did the converse, so let's do the converse here. And the converse with that, this is not true. So the converse is not true, but let me show you why I'm showing you this. So the converse says, if a function is continuous, then it is differentiable. And that is not true. Just because it's continuous does not mean that there's a derivative there. Okay? So this is not true. Alright? Now, I've got this graph here a little bit, and this just kind of shows you what we're talking about. So I want you to notice at first that this whole graph is continuous. I don't have to pick up my point. So I'm going to put a point C here. And if I come down here, this means it's gone over C. And if I find the value of it, this is f of C, or your y value. So the point would be C, f of C. And I just want you to recall continuity. Let's talk about what we learned in continuity from before. The first thing is we knew that it had to be defined at x equals c, which it is. There's a point there. And the second thing to recall is if we did the limit as x approaches c. Now this is a general limit, so I'm talking from both sides that of this function. It's the same as saying the value of that constant, the y value. Okay? So that's just to have as a visual look of continuity. Alright, now when is a function not differentiable? So what I'm talking about here is when is there no derivative at a place, at a point. Alright, so let's find, there's 4 different ways. One is if f of x is not continuous, meaning if I pick up my pencil, so if I come from the left, there's a hole here, and I come from the right, so the limit as x approaches a point from the right does not equal, excuse me, I forgot a function notation here, does not equal the limit as x approaches a from the left, then the limits don't match. It's not continuous. There's no derivative there. There's a hole in the graph. So that's the first time you can say there's no derivative. If there's a hole in the graph, if I pick up my pencil, it's not differentiable. The second one is if it has a sharp corner. And if you look at here, this is the absolute value of x. The derivative from the left is -1, and the derivative on the right is 1, and there's a sharp corner right here. There is no derivative there. There's no derivative there at the sharp corner. If the graph has a vertical line, so there's my vertical line there, the slope is basically of this undefined. There is no derivative there. The derivative does not exist, okay, because of that vertical tangent line. And the fourth one, which is kind of reminds me of the sharp corners, if it has a cusp, and if you'll notice it's coming up here to positive infinity and here, but it's almost like at a point here. See how it's like, they call this a cusp? So it's approaching infinity from both sides. There is no derivative there. So those are the four cases that there's no derivative, it's not differentiable. So let's kind of look at a graph with a little bit of everything. First thing I want you to notice is that this function is continuous everywhere. So the main one that I look at is I try to find a hole in the graph. I don't see any hole in the graph. That's the first place where I'd say, oh, there's no derivative there. So now I'm looking for the other three, a sharp corner, a vertical tangent line, a cusp. And as I follow here, I say, ooh, there's a sharp corner here. So there's no derivative at A because there's a sharp corner. I follow along, this looks okay, come down here, and then I come and I said, oh, at B, looks like there's a vertical tangent line. So there's no derivative at B. This one does not have a cusp, but there are two places where there's no derivative. And remember, the whole function is continuous. Now, graphing the derivative, and I'm going to show another video with this, but I want to kind of get you started here. If f prime of x is greater than 0, so basically I'm saying if my slopes are all positive, which means it kind of goes in this direction, that tells you that your function is increasing. My original function is increasing. If the other way, if f prime of x is less than 0, if my slopes are negative, if you will, so the line kind of looks like this, that means my original function is decreasing. And it's like a clue. It tells you. You can tell by looking at the derivatives. The other way to look at it is the converse. If your function is increasing, then I know all my slopes are positive or my derivative is greater than 0. So this shows my slopes are positive. Here, if f of x is decreasing, or if my original function is decreasing, then all my slopes are negative or my derivative is less than 0. So this is an introduction of the derivative function.